the knowledge base for making good quality holes in composite materials. And then there was a question about the design of the drill point for a specific application. So that was a brilliant idea someone proposed, and then I thought, yes, this is a good idea. We can certainly think, because the same idea we have used for machining of metal matrix composites, but that idea we have not tried in composite laminates. So maybe that was one takeaway from that yesterday's lecture. So every lecture finally ends up with few questions, and then those questions give us few ideas to give to our masters and PhD students for conducting their research work. So to start with, I have a presentation which I gave as a keynote lecture just last week only, in a conference which was organized on advanced materials and manufacturing by Indian Institute of Technology, Indore. So I will like to share the same ideas with all of you in today's session. And before I start and share my presentation, today is, all of you know, is the Christmas. So I wish all of you a very bright Christmas, Merry Christmas, and a very eventful, successful, and satisfying new year 2021. Because 2020 has been a bit of a problematic year for all of us. Therefore, we are having this lecture in the online mode. But otherwise, I would have loved to travel to Banswara, because I love traveling to Rajasthan. I have visited almost all tourist places in Rajasthan multiple times. So it is always a pleasure to be in Rajasthan. And but okay, as the God willing, whatever has to happen, that will happen. But I wish that 2021 is better, even best for all of us. So to start with, I will share my presentation and quickly try to cover the topic, and then maybe towards the end we will take the question answers. Is my presentation visible?
Yes, sir.
Yes, sir.
Okay. So I'll be going to talk about green composite materials, and because many of the experts, today is I think the last day of the FDP. So many of the topics may already have been covered related to natural fiber composites. So therefore, I have given the title as initiatives at IIT Roorkee, because all of you may be by now knowing the concept of green composites or natural fiber based composite materials. So I will quickly touch this topic and try to explain it from my understanding of the concept, and then I will try to show you that what we are trying to do at IIT Roorkee in this area of green composite materials. So to start with, I'll take a different route to explain the concept, because I teach courses related to product design and development, design for manufacturability, product design using value engineering. So my concept is about product design, and in teaching that subject, I normally follow this book, which is given as a reference in this slide, Product Design and Development by Carl Ulrich and Steven Eppinger. And this is a concept which the authors have introduced a few years back, that is design for environment. So all of us are faculty members. We know we teach topics like design for manufacturability, design for assembly, design for quality, design for reliability, design for safety, design for maintenance. But this is something new, that is design for environment, which means that whenever we design a product, we have to understand that how this product is going to affect the environment. Right from the selection of materials to the final disposal, we have to ensure that the environmental impacts of this product are in line with the concept of sustainability. Sustainability means that we are leaving a good environment for our future generations. Therefore, design for environment is a method to minimize or eliminate environmental impacts of a product over its life cycle. Now, what is a product life cycle? That we will try to see in the subsequent slides. But the general concept is that right from the design of a product or the selection of the materials that are going to be used for producing or fabricating that product must be environment friendly. And once the product has lived its life, it has to be disposed of. At that moment also, the product must be dismantled, or it can be shredded, or it can be broken down into various smaller elements which can be put into the environment without causing much harm to the environment. So the effective design for environment practice maintains or improves the product quality and cost while reducing the environmental impact. So deliberately environmental impacts is mentioned in green because normally we associate nature with green. So the next point is that DFE expands the traditional manufacturer's focus on the production and distribution of its products or his products to a closed loop life cycle. So 2 points are to be explained in this. One is the traditional manufacturer's focus. So the traditional manufacturer's focus is take, make and waste philosophy, which means that take the materials, then you produce them using any traditional or a non-traditional manufacturing process, and then finally once the product has lived its life, the product will be treated as a waste. So that take, make and waste philosophy needs a relook from the point of view that whatever you are taking from the environment must be environment friendly, and whatever you are disposing of into the environment, that must also be environment friendly. And in the use also, the product should not have any adverse effects on the environment. So that traditional manufacturers focus needs to change in context of the design for environment. And secondly, we have to ensure the closed loop life cycle, which will be uh, assuring that the materials that we select for product are environment friendly, and once the product has lived its life, the product will be easily uh, managed, or the product will be easily disposed of into the environment without causing any harm, and it will have a natural decay which will be facilitated by the nature, and then after the decay it will get converted into the resources, and the resources can again be used by the engineers or scientists to convert them into materials and then finally the products. So I will show you the closed loop life cycle. So here you see uh, just a minute. So here you see so it is from the same book, Carl Ulrich and Stephen Eppinger. So you see a natural bio life cycle is there, that you have resources, then you extract the resources to convert them into materials, and then these materials are used for the industrial product life cycle. Once the product has lived its life, it is finally after the use, what happens to the product after the use? So after the use, we can ensure that it is reused in any other form or any other different form, or it goes into remanufacturing, or it is going into disposal. So you can see either other approach can be post consumer recycling. So at 2 points, this natural bio life cycle is interacting with the industrial product life cycle. So if we leave this natural product life cycle, only focus on industrial product life cycle, you can see that we extract the materials from nature. We get any material. For example, I am sitting on a wooden chair, so the chair is made up of wood. So wood is taken from nature. It undergoes production. Different processes of woodworking are done on this wood to convert it into a chair. Once the chair is ready, it is distributed through any channels of market, and then I am using it now. Once this chair is used, suppose it is broken, now what can be done? It can be repaired, it can be reused in some other way, or the wood can be used to remanufacture some other product, or it can be recycled into any other usable form, or it can be disposed of into the environment. So this life cycle of a wooden chair is undergoing this round cycle. So at 2 points, it is interacting with the nature. Initially at the selection of materials stage, because we can always make chairs of plastics also, we can have metallic chairs also, we can have plastic chairs, or sorry, wooden chairs also. So at here we are selecting the material, And here the product has already lived its life, and we have to take a decision that how to make use of this product. So these are the 2 points where the industrial product life cycle is interacting with the natural bio life cycle. So these are the two things that we need to take care of when we are designing a product. Now this is the same cycle but with some suggestions in terms of sustainable development or ensuring the sustainability. So here you see that you have a non-renewable resources in the nature. For example, we are using a lot of plastics these days. So these are being used for, which are coming from the petroleum based resources, so which are non-renewable resources. So petroleum based resources, although we are finding new and new sources where we can drill the oil drills and then we can get petroleum, but then still this is one of the non-renewable resources. So what we should do once we are designing a product, we should select the materials which are coming from the renewable resources. That can be any kind of natural fibers. For example, every year the farmers are growing sugar cane. So from the sugar cane also we can get some fibers. Similarly, we are eating banana. So banana fibers can be used, which are the waste banana fibers. So therefore we can focus. I'm just giving few examples that we can use renewable resources as our materials for making the product. And then the other cycle is almost same, but finally at the disposal stage, what we should ensure that we should not put toxics into our environment. At the same time, we should not put inorganics into the environment. So what should we dispose into the environment or the natural bio life cycle are the organic compounds. So if we give back organics into the nature, it will be deposited. The organics will have a natural decay and they will again get converted into the resources. So these resources can be used as a renewable resources, and then we can extract these materials and use them for making any product. So that is the basic concept. So now three things are coming here. First is focus on the renewable resources. Second is only dispose of organic waste into the natural environment and avoid the putting of toxics and inorganics into the environment. So if we focus on these points, we can ensure the sustainable development in which our future generations will also have clean air to breathe and clean water to drink. So that is what with which we have to take our decisions related to the products that we develop. Now, many of you may be wondering that how as engineers or teachers or scientists we can contribute in this endeavor. So normally for sustainable development, there are 3 R's which can ensure sustainability. Maybe that is environmental sustainability, because sustainability also has various dimensions, like sustainability can be economic sustainability, social sustainability, environmental sustainability. So we are majorly focusing today on environmental sustainability. So for ensuring environmental sustainability, we can focus on 3 R's. First R can be reduce, that reduce the usage of resources as non-renewable resources as much as possible. Second can be reuse, which is given in this slide. You see it is mentioned here, reuse. After the use, the product has lived its life, try to reuse it in one or the other way. So the second R is reuse. First R is reduce. So after reduction, you go, that is not possible, then try to reuse the products as far as possible. And even if you are not able to reuse it, then at least recycle it into some other product form. So if we focus on reduction, reuse, and recycling of the products that we are using, we will be contributing towards the sustainable development. So I will try to relate my talk with in context of the composite materials and how they can help us to achieve this target of ensuring sustainable development. Now, what can be the conditions for sustainability? I have already explained in the previous slide that eliminate the use of, this is just the revision or the summary which I have shown in the previous slide, that is conditions for sustainability. So eliminate the use of non-renewable natural resources, as I have already given one example. Eliminate the disposal of synthetic and inorganic materials into the nature, and eliminate the creation of toxic waste that are not part of the natural life cycle. So if we can do these things, not in totality or ideally, but partially also, we will start seeing the effects of the cleansing of the river waters or the improvement in the air quality index. So therefore, if we take minor steps, baby steps, one step at a time, we can slowly see the effects coming in the next 5 to 10 years time. Now, since my topic is on green composite materials, so the composites, this course is on composites. So many faculty member may have already given the classification that how the composite materials are classified based on the matrix, then based on the reinforcement, how you classify. So my talk is related to polymer matrix composites. So I am not going to discuss about the metal matrix composites and the ceramic matrix composite. So if we talk about the polymer matrix composites, many faculty members, distinguished speakers during the course may have already highlighted that these composite materials have huge application spectrum. So I agree that we have a huge potential for using these composite materials, but the only challenge is that the government has now, sorry, that the government has identified plastics as a challenging material, because if you see on the slide, only 9% of the plastic waste is recycled. About 80% is accumulated in landfills, dumps, or natural environment. So therefore, or the 12% is incinerated or burnt. So if the current trends continue, our oceans would contain more plastic than fish by the year 2050. So that is one big challenge, because the researchers have found out that when the plastic is dumped into the oceans, it gets converted into microplastics in few years, few hundred years. So that microplastics are taken as food by the fish, assuming that this is a smaller fish, but then that is plastic, and then if the fish eats that, she is not able to digest, and then finally it enters into our food chain. So therefore, we should be very careful about disposing of plastics into the oceans also, because from there it can enter into our food chain. So therefore, these are the challenges related to the plastics. And in the slide you can see, this is a river in China which flows past Shanghai, and it delivers 1.5 million tons of plastic waste into the Yellow Sea. So therefore, this is a challenge which we need to overcome. And this is the summary. These are some few first pages or the cover pages of some magazines which have already highlighted the importance of reducing the use of plastics, or development of plastics which are biodegradable or which are friendly to the environment. So the pollution due to plastics has attained the level of a man-made disaster, and somehow we have to overcome these challenges. And similarly, for composite materials also, I will show you that once you are producing a composite part, there is a generation of waste during the production stage also, as well as once the product has lived its life or the intended life, at the end of life also that product needs to be either recycled or reused. So those kind of waste is a challenge. Normally, once we start doing research in the field of composite materials, our focus is to develop a composite material, identify a process, then make the samples, and then characterize them, test them for their mechanical behavior or the tribological behavior or the machining characteristics, or we these days study the environmental behavior of that composite materials. So we have different directions of research, but the efforts toward the end of life strategies that can be adopted for composite materials is also equally important, because we can justify the use of composite materials that yes, these are very lightweight materials, these can be used for aircraft industry, these can be used for automotive industry, and they can even beat metals in certain characteristics. So all those goody things are very well taken, and therefore they are finding applications in large spectrum of engineering fields. But with passage of time, someone has to, or some groups of people have to see that how what will happen to these materials once the life is over. So how to manage the plastic waste or the composite materials waste is also one research area which can be identified by young researchers and can be explored. And this has a lot of potential, because at the end of life we have to see that how the product will be managed. And therefore there are world level also World Environment Day is celebrated. And if you see, I have taken the themes, one of my PhD students made this slide. So the last 3 years theme is mentioned here. In 2018 it was last 3 years theme is mentioned here. And in the year 2018 the theme was beat the plastic pollution. And in 2019 you can see the theme was beat the air pollution. So here you can see I have already told that three R's of sustainable development are reduce, reuse and recycle. So here you see the same theme is mentioned. If you can't reuse it, refuse it. So reuse is one thing, that either we have to reuse the things again and again, then we have to reduce, and if the refuse will automatically lead to reduction in the use. That if the product cannot be reused, then you don't use that product, which means that you refuse it. And if you refuse it, automatically it will lead to the reduction in the use. So that is reduce. Then the second 2019 you see beat the air pollution. And in the previous slide I have shown that 12% of the plastic is incinerated for extracting some energy, but that may lead to a severe air quality problem. So therefore, if to beat the air pollution also, if we are able to manage our plastic in a better manner, that will help us further. And then this year to 2020, although 5-6 days are only left in this year, but during the World Environment Day, the focus was on time for nature. So if you see that on Environment Day, we are always having a theme which is helping us to identify the area in which we should conduct our research. And one of them is the reduce. That is how we can reduce the use of materials which are coming from the non-renewable resources, and then either we can reuse it through recycling. So I will try to focus on both these aspects. So how we can reduce? So we can reduce the use of plastics by incorporating some natural fibers or fillers into the plastic products. So if suppose the product is made up of 1 kg, it is a 1 kg plastic product. So if we are able to put 300 grams of natural fibers into that, so then 30% of the reduction is there in the use of the plastic. So that can be one idea without compromising on the performance. So we are not going to compromise on the functional requirements, aesthetic requirements, or the other special requirements from that product. But only thing is, from the material selection point of view, instead of using 1 kg of a polymer, we are going to use 700 grams of polymer and 300 grams of natural fiber. So that will lead to the reduction. So that is the theme that you see, that if you can't reuse it, then refuse it. So we cannot directly refuse, but slowly we can try to tailor or try to make our product with those materials which can be environment friendly. Then the second, or reuse. So from reuse point of view, we can recycle the material again and again and again. So these solutions lead to the topic, that is the natural fiber reinforced polymer composites, or in summary we can say as the green composite materials. So what we are trying to do on the screen, if you have a look, I have put all the images there. So we are trying to, at IIT Roorkee, we are trying to develop the composite materials using the natural fibers and the bio-based polymers. So we combine them together. Some of the processes that we use, I'll explain in the subsequent slides. So we are combining natural fibers and polymers and converting them into the specimen, and then we are testing these specimen to find out that are the application areas where these materials can be used. I will show you maybe some of the products that we have fabricated using these natural fiber based materials. Then we are also conducting in service performance analysis of these materials, that how they will behave under the ambient conditions over a period of 6 months time, or how they will behave under the accelerated aging conditions where we expose them to -8 degree or -10 degree for 12 hours duration, assuming that we are using this product in an area where the temperatures go less than 0 degree centigrade, and then we expose them to maybe 60 or 70 degree centigrade for the remaining part of the day, that is 12 hours, and try to analyze that over a period of 6 months time, what is the change in their properties or in the color of the material. So exposing them to extreme conditions like sub-zero conditions and +45 conditions, we are trying to analyze that how these materials will behave, and that work already we have published in Composites Part B, and those who are interested can read that work, that how this analysis was conducted. And then we are also conducting research in the area of end of life, or once the product has lived its life, how we can decompose it, in what kind of condition, what kind of soil we should use to decompose it, for decomposing this material, and after how much time the material will degrade, how it will degrade, what are the steps of degradation. All that we are trying to analyze at the end of the service life of the composite or the green composite material. And also we are trying to see that if the product is a thermoplastic based composite or a thermoset based composite, how we can recycle it. So that aspect also we are touching. So some work we have already accomplished and published also towards the recycling of thermoplastic based composite materials, but now we are also thinking that lot of the products of composites that we use are thermosetting based composite materials. So can we do something related to the recycling of the thermoset based composite materials also? So all these aspects we are touching, and I will try to touch each one of these in the maybe the next half an hour time, and then we will try to take question answer so that we are able to address some of the doubts which have come from this talk. So basically this image I have put deliberately, ensuring that we have to ensure a circular economy, that whatever we take from the mother earth, it should be again given back in the same form or the better form, so that it is accepted and again it undergoes the natural decay, and finally we get the final resources which can again be used as materials for making the product. So these are the aspects that we are touching. So I will start from development and then I will end at recycling. So first is we have to reduce the use of the polymers or the use of non-renewable resources. So how we can do that? So for that, this slide may have been shown to you by a number of speakers during the last 4 days. So every composite material will have a matrix and a reinforcement. But here you see all the reinforcements are synthetic reinforcements. So we are trying to bring into picture the natural reinforcements in terms of natural fibers, which I will show you in the subsequent slides. And then you have thermosets and thermoplastics, which is classification of the polymers. So you can have either a thermosetting polymer as a matrix material or a thermoplastic material as a matrix. These are the application. Many of the speakers may have already shown you this. But what we are trying to do at IIT Roorkee is that we are trying to develop biocomposite materials using a biopolymer and a biodegradable fiber. So when we combine these two together, we get a composite which can be termed as environment friendly. So it can be environment friendly on different scales. So the major areas of our research in this broad spectrum of natural fiber based composite materials is that we are trying to select the raw materials which are coming from renewable resources. For example, the natural fibers or the biopolymers. So whatever materials we select for making the product, they must come from the renewable resources as is suggested from the design for environment guidelines. So if we follow the design for environment guidelines, all of you will remember in the very beginning of today's session, I have shown that from design for environment point of view, we should minimize the use of materials coming from non-renewable resources, and we should maximize the use of materials derived from renewable resources. So we are focusing on renewable resources. Then finally, we are trying to understand the recycling behavior of the composite materials, and then we are focusing on the biodegradable or biodegradability of the developed composite materials also. But all that cannot be only achieved at the lab scale, because if we develop a new material, we have to take it to the market, so that we have a huge user base which can make use of that material or consume that material in various engineering applications, and then it leads to a subsequent reduction in the use of materials derived from non-renewable resources. And for that we have to establish the commercial viability also. We have to scale up what we are trying to do at the lab scale to the commercial scale. And also there are various classification techniques, methods that or government regulations or government approvals that have to be taken before we claim that this material is environmentally acceptable. So the major objective of our research efforts at IIT Roorkee is to develop sustainable composites. Now, what are these composites? These composites are renewable, recyclable, biodegradable, and they are having their environmental acceptability, and commercially also these can compete against the already established composite materials. Now, I told you that I will go to a slide where we will try to understand the natural fibers. So this many times the learners have this question that how we can classify as a fully green or partially green. So as you all of you know by now that in composite materials you have two constituents. One of the constituents is called as the matrix, the other one is the reinforcement. So if both constituents are derived from natural resources, in that case we can say that it is a fully sustainable material or a fully green composite materials. But if one of the constituents is natural, the other one is synthetic, in that case we will say that it is a partially green composite. It is not a fully green composite because one of the constituents is still synthetic. So these slides give you a good summary of classification between a fully green composite and a partially green composite. So if you see that if you are using a non-biodegradable polymer like epoxy or polyester and a synthetic fiber like carbon or a glass fiber, so you combine these two together, you will get a non-biodegradable composite. But on the other case, suppose you are using the sugarcane fiber or the bagasse fiber with a natural or a biopolymer, then in that case that material will be a fully biodegradable composite material. But that transition has to take place, that the image of the aircraft that was shown in today's presentation, most of the materials that were used were synthetic fibers with non-biodegradable polymer. So that is now the old practice because the materials have good strength. They are used in aircraft industry, automotive industry, and a host of other applications also. But now from the sustainability point of view and from the environment friendliness point of view, the researchers are now focusing their attention towards the development of materials which are friendly to the nature. So that transition is not that easy because there are number of challenges that we have to address before we get a fully biodegradable materials which are able to compete with very good high strength materials that are possible with, or the products possible with, synthetic fibers and non-biodegradable polymers. So this is the research trend now. Many researchers, not only in India but also abroad, are now focusing their attention towards development of fully biodegradable green composite materials. So what is our objective to reduce the use of polymers or plastics? So we are trying to develop processes. So all these processes are well developed and we are able to successfully fabricate composite materials based on these processes. So this is one case study that is of pineapple fiber. So the processes are explained here, but we are starting from the extracted fiber. We don't go into this stage. We get the fiber from the company and then we do the four important processes of chopping, soaking, drying and sieving, and finally we pack it into the airtight packages so that these fibers can further, they do not absorb any moisture, and then can be used for using any of the processes that are mentioned in the previous slide. Here you see we have developed three processing strategies or routes: direct injection molding, extrusion injection molding, and extrusion compression molding. So for that we require fibers. This is just one, because the team at IIT Roorkee, our PhD students have worked on different types of fibers like pineapple fiber, banana fiber, sisal fiber, jute fiber, bagasse fiber, hemp fiber, grevia optiva. So we have used different types of natural fibers as reinforcement in different types of polymers also. From the thermosetting family, we have investigated using the epoxy, we have investigated using polyester, and from the thermoplastics family, we have investigated using polypropylene, polyethylene, and different variants or different, you can say, codes of the different polymers. So using blended polymers also. So we have used different types of polymers both from thermosetting and thermoplastics family, and we have made composite materials. Now this is you can see the materials that we have used. This is one case study. Just I am taking to explain the concept. So we can use a natural biopolymer, which is polylactic acid, and then we can use a synthetic polymer, which can be polypropylene, then banana fiber and pineapple fiber. These are the way the pellets would look like. These are PLA pellets, these are polylactic acid pellets, these are polypropylene pellets, and then these are combined with the fiber. So normally we get the fiber in this form, and then we convert it into this short fiber form, and then we make a batch of polymer and fiber together, and then use it as a raw material for making the composite materials. Now this is the mold that we have designed in-house and fabricated, through which we can fabricate tensile testing sample. As you can see, tensile testing sample, it is made in cavity 1. Flexural testing sample is made in, specimen is made in cavity 2, and impact test sample is made in cavity 3. So in a single shot, we are able to produce three specimens as per the ASTM standards, as you see here. Now, what is the process that we follow? Now, this is the direct injection molding process, where we combine the fibers and the pellets together in the hopper, and then we extrude them through the barrel, and then finally it is injected into the mold cavity, and finally we get the samples like this. So this is why it is called, why the word direct is added, because directly we are feeding the fibers and the pellets into the hopper, and then through the barrel using this screw feeder, it is fed into the, or it is injected into the mold cavity. The mold cavity already I have shown you in the previous slide. So in a single shot we are able to produce 3 samples. So the samples are shown here, the bigger samples. These are tensile testing samples. These are 3 samples. So you can see that the fibers are uniformly distributed all along the bulk of the matrix. So the matrix can be polypropylene, it can be polyethylene, it can be high density polyethylene, it can be polylactic acid. So any thermoplastic polymer can be used with natural, and the fibers can also be, we have made fiber samples with sisal fiber, we have made samples with aloe vera fibers, we have used bagasse fibers, banana fibers, pineapple fibers. So a wide variety of fibers we have experimented with, and different types of polymers, and this process is well established now globally, that can be used for making the composite samples. So this is another process that we have developed at IIT Roorkee. So the injection molding remains same, but we now extrude the samples. Now first we extrude the samples. This is the composite strand, that is extruded strand, which can also be called as extrudate. So we have fibers and pellets here, which we combine together in the hopper, and from the hopper we extrude this material using the various heaters. The pellets melt and the fibers are encapsulated or impregnated with the polymer, and then this combination of fiber and polymer comes out as a composite strand or extrudate, which is cooled down and finally pelletized. Pelletized means we cut it into a standard size or composite pellet. So these are the composite pellets that you see on your screen. So this pellet now has been both the fibers and the polymer, and these pellets are then used as a raw material in the injection molding machine, as you can see here. Now in the previous process we were talking about direct injection molding. We can put direct fibers and polymers into the hopper, a batch of fiber and polymer into the hopper, and then we directly inject it to get the samples. But here, instead of putting the fiber and the polymer directly into the injection molding machine, we are putting it into the extruder, and first we are extruding a composite strand and pelletizing it to make the pellets, and these pellets are now being used as the raw material for injection molding process. So here we are using two processes, that is extrusion and injection molding, and therefore we are calling it the process as extrusion injection molding. And finally we are able to make the samples like this. So these are the samples, and if maybe I can show you some of the samples which are already available. So this is one sample. If possible, you can see in the camera, this is one sample. I think the presentation, okay, towards the end of my session I will show you the samples. Then instead of pelletizing here, if we change this process here, after pelletization we collect this extrudate into a mold, then we can call the process as the extrusion compression molding process. So here you can see, in extrusion what we are trying to do, we are trying to collect this extrudate in a preheated mold. So this is the same process of extrusion, but here we are not pelletizing or cutting the composite strand or the extrudate into the composite pellets, but we are collecting this in the preheated mold. You can see here, this is the actual picture, that the material coming out from the mold or the die of extrusion machine, and it is getting collected. Here it is just being collected, but normally once we have to do extrusion compression molding, we collect it in a mold, and then that mold is transferred to the compression molding machine. This is our industrial scale compression molding machine, and once this plate is ready, it is taken out from the by opening the two halves of the mold. So we have a mold, designed a mold which can give us a composite plate of 30 centimeters by 30 centimeters, or 300 millimeters into 300 millimeters, and the thickness can be maximum 6 millimeters. So that mold we already have for our compression molding machine, and therefore we are able to form the plates, composite plates like this, where the fibers are distributed all along the polymer matrix. And yesterday, after my lecture, there was a question that how we can fabricate the continuous fiber, because you are talking about the short fibers only. So for continuous fiber composite material, this process is widely used, where we can use the composite in forms of woven mat. So we can have a jute fiber or a sisal fiber woven mat, and it can be used as a reinforcement for different types of polymer. So compression molding can be used for making continuous fiber reinforced composite materials. So this is a composite plate that we were able to fabricate. Now why I am calling it a plate, because the fibers are short fibers and they are uniformly distributed in the polymer matrix. So if we use continuous fibers in the form of different layers, maybe 4 layers or 6 layers or 8 layers, in that case we will call it as a composite laminate, because there we have laminated different layers of fibers with polymer. Now these are the fabricated test specimens at optimal parameter setting. So you can see direct injection molding samples, extrusion injection molding samples, and extrusion compression molding samples also. Now some of you may be wondering that why this angle is there. So I told you that in our single shot we make 3 samples. One is a tensile testing sample, another one is the flexural testing, and the third one is the impact testing sample. So therefore, finally, we cut this specimen from that larger sample that we get, which has 3 samples. So this is the explanation here. This is the common area. On one side of the mold, we get the flexural and the impact, and on one side of the mold, we get the tensile testing specimen. So in a single shot, we get the 3 samples. And here you see the effect of fiber loading, that without any fiber, you get a purely white sample, or a specimen with 10% fiber. This is 10%, then 20%, and with 30%. So we can integrate different weight percentage of fiber and see the effect on the different properties of the developed composite materials. So this is a schematic distribution and alignment, because I told you that now we can investigate the properties, that which type of composite or which type of process is giving the better performance or better mechanical properties. So then we have to see that you are making the same sample, same size, same fiber, same weight percent with direct injection molding. Same type of polymer is used, same fibers, same weight percentage, but the process is now different, that is extrusion injection molding. And so same, all other factors remaining same, only the process is changing. So why, what is the effect of this process on the mechanical properties of the developed composite? So that also we have investigated and tried to explain using the schematic diagrams like this, that once the composite melt flows, or the fiber and the polymer melt flows in the mold cavity, how the fibers get aligned in a particular direction, and what is the fiber distribution and orientation in the core area, what is the fiber distribution and alignment at the surface of the composite developed. So the fibers near the surface of the mold are aligned in the flow direction, whereas they are aligned randomly at the core region. Now what can be the reason for this? Because we have the frictional effect of, because of the mold walls, that are the metallic mold walls, and therefore the fibers may get aligned at the velocity at which the flow, melt flow is flowing, will be different at the surface as well as at the center. So therefore we have to see and establish that why the mechanical properties are different for the three different processes. So this work also we have completed, and all the results have been already established and published in the journal. I think in the next few slides you may find the reference to that journal also. So the final summary that we have found out is that an improvement in the distribution and orientation of fibers during the EIM was observed. So EIM, all of you know by now, is extrusion injection molding. So using the extrusion injection molding process, we were able to get better quality, not in terms of the surface finish, but better performance in terms of the mechanical properties of the composites. These are some of the actual images of the samples made by different processes: direct injection molding, extrusion injection molding, and extrusion compression molding. So the polymer here is polylactic acid, and the fibers are the banana fibers, and fiber loading is 20 weight percent. And you can see the reference here. This work has already been reported and published in Composites Part B, Engineering. So these are some of the, this I will try to show you after my session today. I just try to check the time, that it is going to be 1 hour. So these are some of the samples that we have made. These are some of the products. This is the actual product. I will show you towards the end of my class. And these are the modified products with 30 weight percent of sugarcane fiber. And this is the back part of the chair. Now this is the first part, that is reduce. Now reduce means that instead of using 100% polymer, we can use 60, 70, 80% polymer, and at least 20-30% can be coming from the natural sources, which are otherwise classified as agricultural waste or sometimes forest waste also. Now how these can be used for reducing the use of non-renewable resource like polymer, we have seen in the previous slide, starting from the concept to the process and finally the product. So I have shown you some products. So these are not the only products. Our students have further developed few products which are coming from natural fibers and recycled plastics also. So those products were like a pen stand that can be used, or a chair which can be used for sitting. So that was developed using epoxy and jute fibers. The chair was developed, which is displayed now in the Design Innovation Center. So a lot of products can be made using these natural resources, either at the matrix scale, matrix level, or at the reinforcement level. So out of the two constituents, ideally the both the constituents, but even if you are able to replace one of the constituents of composite materials with an environment friendly substitute, that is also your contribution towards reducing the use of non-renewable resources. Now coming to the reuse and recycling, quickly in next 15 minutes I will try to cover this. Then we will have a question answer session. uh, Jignesh, my session is 1 hour or 1.5 hours.
No issue, sir.
No, the participants should not feel that I have exceeded my time.
No, sir, no. That is not problem, sir.
Okay. Okay.
Sir, you can sir continue for 1.5 hours.
Okay. 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 I will try to cover in 20 minutes, and then finally we can have some time for question answer. All right. Thank you. So second part of my
Sure, sir. Yeah.
yeah, thank you. Second part of my talk is related to reuse and recycling of the polymer composite. So this I will try to cover now. Now, this is not related to green composites, but it is related to carbon fiber composite material, which many of the researchers may have already talked to you. So how we can now reuse these materials? So here you can see you start with the structural component at the aerospace level. So you use it for aerospace application, and then you recover the carbon fibers from there and use it for some low strength application, which can be automotive or slowly moving towards the non-structural applications, which can be automotive. Then finally you come down to some applications where the carbon fiber is then used in the particle form, or it is shredded into small fibers, and then it can be used in the thermoplastic with the powder filler. So the carbon fibers are here used as a powder filler, that you see small dots of carbon fiber. So at first stage, the carbon fiber is used in the structural component at aerospace level, and maybe after 3-4 recycling stages, it can be used as a powder filler. So that means that we can ensure that the fiber that we are developing, or the carbon fiber that we are producing, is not put as a waste material after single use only. We can recycle it and reuse it number of times, but the application may change. So initial applications may be aircraft applications, but final applications can be, as we see, a non-structural component where it is used as a filler, or a carbon fiber filler is used in the thermoplastic matrix. So we are going from a structural component to a non-structural component. So fiber reinforcement type will change. Here we have continuous carbon fiber, but here we have short carbon fiber as a filler. So we have, you can see now, I will read it for you. The references are also given. It is representing, this image is representing the flow process of reusing. So I told you that we have to focus on reuse and recycling also. Reuse the recovered fibers from a high cost aerospace composite component. So this is a high cost component used in an aircraft, to a low cost non-structural component. So this is a thermoplastic film with powder filler of carbon fibers in the powder form. So this is a low cost non-structural component. So from a high cost, high strength structural component used in aircraft industry, we can recycle and reuse the carbon fiber in a non-structural low cost component. So I think the concept is well explained here. So the recovered fibers from the carbon fiber reinforced plastic waste are used in applications that require less stringent mechanical performance and lower cost than the pristine or virgin carbon fibers. So then we can see that if we start reusing, recycling our carbon fibers, we can even get some applications where the strength is not a big issue, the mechanical performance is not a big issue, but still we can use the functional characteristics of the carbon fibers. And this is from this paper, that is 2020, which is not a very old paper. This is this year only latest paper, which is published by Hao Wang. I know personally, he is the chief editor of this journal. So you can see that in 2020 also people are focusing on these aspects of recycling and recovery. So these are the this is a slightly busy slide. So I have already shown you a closed loop, starts from the aerospace unidirectional FRP structural component. Recovered chopped fibers are pressed to form a sheet molding compound, which can be used in automotive structural part. So right from unidirectional carbon fiber reinforcement from aircraft industry, we are now using it as a sheet molding compound in automotive, but still it is at the structural level only. This part can be further recycled into non-woven short fiber SMC with lower fiber volume fraction to form a semi-structural component suited for automotive and marine application. Next stage is these can be further reclaimed and used as powder to reinforce the thermoplastic matrices through the injection molding. So the resultant components being suitable for low load bearing structural applications in mass transit. So right from the unidirectional carbon fiber being used in aircraft industry, we are coming to a low load bearing structural applications in mass transit. So over a period of time, by reclaiming and recycling and reusing the derived carbon fibers from the composite, we can use them multiple times for multiple applications, ranging from high strength, high stiffness applications to low load bearing structural applications. So therefore, if the recovered carbon fibers can be used multiple times, similarly the recovered natural fibers can also be used multiple times, and this type of work can also be initiated by researchers. Now, this is slightly a busy slide focused on again the economically sustainable waste management for carbon fiber, because carbon fiber based composites are used in a wide variety of applications. And now initially when the composites were developed, most of the aircraft applications were based on carbon fiber only, and now these products have already lived its life. So now the researchers are trying to establish strategies that how we can manage this CFRP waste, and therefore a lot of work is being reported in this direction. And both the articles you see as a given reference are not very old articles, 2017 or 2018 and 2017, so hardly 2-3 years back this type of work is being reported. Now, I want to give you a brief idea about how these can be recycled also. So there are common granulators are available through which you can shred or cut these composite waste into pellets. So this is the most mature non-toxic CFRP recycling method, and it involves multiple steps to reduce the size of the CFRP waste. So whatever carbon fiber reinforced plastic you are using either in the aircraft industry or in the automotive industry can be crushed into smaller size granules or pellets using these standard granulators. So composites are pulled apart, which means they are broken down, shredded to 50 to 100 millimeter size, and further grinding or milling is applied to obtain the recyclates with different sizes that range from fine powder to fibrous recyclate. So which means that you can decide that what is the size of the recyclate that you want to produce using this granulator, and what kind of grinding and milling operation you want to do to finally bring that into either the powder form or to a smaller size form with which can have few fibers also in that. So attain 50 to 65% of the tensile strength of the virgin carbon fiber. So the first use of the carbon fiber which was there for the aircraft industry, so we can still get 50 to 60% of the tensile strength of that fiber which was used for its virgin state, that is in the first use when it was used for the aircraft industry. Secondly, it was used for the automotive industry. So with steps of recycling, the tensile strength will definitely reduce, but still we are able to achieve 50 to 65% of the tensile strength. Now, if we talk about the previous 2 slides or 3 slides were focused on the recycling strategies or the waste management strategies for carbon fiber reinforced composites. But what can be the challenges with natural fiber composites, either in use or after the end of life? That I have tried to summarize, because this will give our audience an idea that how and the way they can conduct their research in this area. So the major challenges associated with natural fibers as reinforcement are the incompatibility between fibers and polymers, because all of you know natural fibers have a tendency to absorb moisture. They are hydrophilic in nature, whereas most of the polymers are hydrophobic in nature. So either we have to make the polymer as hydrophilic so that they can have a good understanding with the fibers, or we can reduce the hydrophilicity of the natural fibers to make them compatible with the polymers. So though that requires either the blending of polymers or the treatment of the natural fiber. So different strategies can be investigated to blend or to mix the fibers and the polymers to get good interfacial behavior that will lead to better or the best mechanical properties. Another problem while processing is the tendency to form the aggregates. So once you are making the composite materials, there is a tendency that the fibers, because of the uh, different surface characteristics, they tend to be friendly with each other rather than being friendly with the polymer. So that also is a challenge, that the fibers may try to make their own smaller group and then they do not bind well with the polymer. So we have to treat the fibers in a way that they are not able to form an aggregate or do not agglomerate in the polymer matrix. Already I have told you that they're hydrophilic in nature, so the moisture resistance of natural fibers is normally not very good. And also we know that wood we are using for fire purposes, and wood is also one kind of a natural fibers. Therefore, we see that the fire resistance characteristics of composite materials are also not very well established. The researchers are now trying to integrate some fillers which can act as fire retardants in natural fiber based composite materials, because natural fibers have tendency to catch fire. Also, the next challenge is that the temperatures that we can use for fabricating the composite materials. Now, that is also a big challenge, because all of you know that glass and carbon can be processed at very high temperatures, but natural fibers cannot be processed at very high temperatures. We have seen that decoloration of fibers take place, even burning of fibers take place at high temperatures, maybe around 400, 500 degrees centigrade. So therefore, based on the processing temperature that can be achieved for natural fibers, we have to limit certain processes. Also, the durability is important, because mostly in the rainy season we see that the wooden doors normally have a tendency to swell because of absorption of the moisture by the fibers. Therefore, the durability also needs to be ensured, that how these natural fiber-based materials can sustain longer lifespans. So these are some of the hints which can be taken by the researchers towards the research efforts in the field of development, characterization, and establishing commercial viability of natural fiber-based materials. Now, this is another important aspect that we are touching about, the recycling of polymer composites. So these are the samples, as I told you, that as per our mold, we get this three samples in a single shot. So there are number of samples that you see here. So this is the tensile testing sample. We will cut it from here and we will get one tensile testing sample. Then this is a flexural testing sample, and finally we have an impact testing sample. So we use different samples for different types of characterization. Now if you see here, this is the sprue through which the material enters the mold cavity, and these are the waste. This material, we cut the sample from here. This is the flexural sample, this is the impact, and this is the tensile. So once we cut it, this material, all you see here, all the sprue, this is the waste material. Now this is normally, we have seen that it is 10% of the overall weight of a single sample. So this is one shot, we get this, and out of this, if we calculate the weight of this sprue, this is 10%. Now what to do with this waste? It is a process based waste, because it is a manufacturing related waste. What can be done with this? So what we are trying to see, we are trying to establish that how much change in the mechanical properties take place if we recycle this waste material. So this is the process waste that you see here. So if we recycle it, therefore I have explained the process of using a granulator also prior to that, so that you are able to appreciate. Now this process waste can be put into a granulator and can be made in the form of fine granules, which can again be used as a raw material for injection molding process. And after injection molding, we can get this type of recycled composite specimens. So once we get a recycled composite specimen, again we can take this material from here. It has undergone a recycling, and again pelletize and granulate, use the granules to go make next series of samples, and again from there we can get this material as process waste, and again do the next recycling. So we have done this number multiple times and established that what is the change in the mechanical properties that happen if we recycle it multiple times, and the results are there on your screen. So normally if you see, we are talking about polylactic acid here. So the tensile strength of neat polylactic acid is 54 megapascal as supplied by the vendor who has supplied the polylactic acid pellets. And if you see that after adding fibers, short fibers also, normally we don't integrate short fibers for improving the strength of the matrix, but here if we see, even with short fibers also the strength is improving. For example, you can see here the 54 is marked here in blue color. So 54 is the tensile strength of the neat sample, but if we integrate fibers into this, we can get tensile strength much higher, as well as the tensile modulus much higher than what we get for the neat polylactic acid. So the first conclusion that can be drawn from here is that if we add fibers into the polylactic acid polymer, we will be able to improve the tensile strength. So here you see this is the fiber, and here you see the improvement in the tensile strength. Then after first recycling, as I showed you in the previous slide, that we can recycle the process waste multiple times. So after first recycling, although the properties are reducing, but still these are more than the neat PLA. So even after 5 stages or 5 levels of recycling, the strength that we achieved, or the tensile strength that we achieved for uh, fiber reinforced polylactic acid composite is still more than the PLA. So which establishes the fact that these materials are recyclable. We can recycle them multiple times and achieve properties which are better than the neat polymer. So which means that any product that we are using which is made up of only polymer, if we put fibers into that polymer at the fabrication stage only, so that fiber will not only improve the mechanical properties of that polymer, but also help in the recycling aspects also. We conclude from here that the number of cycles it can be recycled may vary from the fiber and polymer combination, but for this case study we have seen that even after 5 recycling steps, the material can still be reused for certain applications. So as I have shown in the slide, where the carbon fiber was recovered and reused for multiple applications, starting from a high strength, high performance aircraft application to a non load bearing thermoplastic based filler application. Similarly, the natural fiber based materials can also be recycled multiple times from a high and high performance application to a low and non load bearing application. So therefore we can say that if we talk about the recyclability, if we talk about the biodegradability, if we talk about the selection of materials from sustainability point of view, then these natural fiber composite materials have a long way to go, because these materials will certainly lead to the reduction in the use of polymers or the non-biodegradable polymers. They can be recycled multiple times, and even we have done the studies related to the biodegradability also. So there also we have seen that these materials are easy to degrade under the standard conditions of decomposition or standard exposure to soil barrier. So therefore soil burial is not a difficult task. So if we can decompose them, they can be easily degraded. So therefore these materials present as a huge potential to be used in various engineering applications. So finally, from the research point of view, we try to understand the behavior, that how they are degrading, what is the kind of bonding between the fiber and the polymer, whether the cracks are appearing, whether the fiber is degrading first or the polymer is degrading first. So all that can easily be established with the help of the scanning electron microscopy. And I think I will stop here. I want to show you some samples, and before that I will try to stop my presentation or stop sharing, so that I can am I visible? Okay, I want to show you some samples that we have made Like this is one sample, if you can see, with natural fibers. Is it visible?
Yes, sir. It is visible. Yes, sir.
So this is one sample. Then I will try to show you the product also. This is one standard joint. If you can see, lap joint made
Yes,
by
sir.
the ultrasonic welding without any additional material, because it is thermoplastic, it can be processed again and again. This is with natural fibers and thermoplastic polymer and a joint. It is a strong joint, it cannot be broken.
No additional material is added, sir, in
No
between this.
additional material is added in this. There are two samples are taken, independent samples. They are put under the ultrasonic probe, and then through the ultrasonic vibration, this heat is produced at the interface and the joint is fabricated. It takes less than a second to make this joint. Normally, if you use adhesive,
In
normally if you use
heating is provided, sir.
heating,
Heating is required, or it is in the
no,
normal?
nothing is required. Heat is produced by the ultrasonic vibrations.
Okay.
So no heat is required. So it takes only the time required for setting it under the ultrasonic transducer. That will take some time, maybe 2 to 3 minutes, but the actual process takes very less time. It is a very fast process of making a joint with natural fiber composites. You can see it is good joint. And this is the product that I have shown the image. This is a polypropylene plastic part, pure polymer. And we have converted it to this part.
Yes, sir.
It is a natural fiber, sugarcane fiber, bagasse fiber. And similarly, the back part of the chair. So therefore, what I want to point out is that there are a lot of applications where these natural fibers can easily replace some of the products that we are already using, which are either pure polymers or with natural, not with natural, but with carbon or glass fibers, but are being used for non-structural applications. So there, in that case, we can always put natural fibers in place of synthetic fibers, or if it is a pure polymer part, then it is even easier to replace some of the polymer with the fiber. So we have seen the properties also improve, the mechanical properties improve, the recyclability is easier. So we can recycle them then multiple times. So that also we have seen, and even degradability also we have seen that it is easy to degrade if you have much more natural fibers in the polymers. So I think with that I will close. If there are questions, then we can have few questions now.
Sir, as we are preparing three sample in one shot, so all the sample have a same property, or so fiber volume fraction maybe some maybe vary.
No. Fiber volume fraction is common in all the three. So that we have ensured after doing multiple levels of optimization, because I have explained only the best parts. So I have served you the juice in the glass. So all the peeling up of the oranges, removing the natural fibers from the orange, that work already we have done. So I have given you the final output in terms of that these are the good quality samples. But before we get these samples, many times the mold was not completely filled. Sometimes the nozzle was choked with the natural fibers. We
Yes.
had to redesign the nozzle again and again. So a lot of trial and error was done to find, and finally the temperature was not sufficient enough to get the complete filling of the mold. Sometimes the pressure was not enough and there was warpage in the samples. So there were, and with persistence and perseverance, the students kept on working, and now at least we have identified a broad range in which we have to work, and whatever optimization has to be done is done within that range only, so we hit the target now easily. But the previously 4 5 years back, the students who were working, they had to toil very hard to bring that range, that this is the range in which most of the polymers and natural fibers will work. So now the fibers also, as all of you may, someone may, some other faculty may have already taught that in natural fibers you have different constituents like cellulose, hemicellulose, lignin, pectin. So that where that constituents may vary from one natural fiber to another natural fiber, but broadly from the processing point of view, the variation is not that high in terms of the temperatures at which they can be processed, in terms of the fiber volume fraction at which can be input into the polymer. So those things are more or less in a broad range. So that range now we have already established over the last 5 years or 6 years time. So now our students are easily able to, with less efforts, now they are able to achieve the optimal setting for a different. Even if we today we start working with a different natural fiber, I am hopeful that within a month or a 2 month time, we will be able to establish the optimal conditions for making the good quality samples.
Yes.
And the
Thank you.
fiber volume is constant. It is constant in all the 3 samples.
Yes, sir. So if you have any question, you can unmute yourself and you can ask if you have any question about the manufacturing and about the natural fiber. Uh, Sir, I want to ask one last question.
Yeah, please.
As you made one composite for the Godrej company.
Yeah.
So they asked you to make that component or replace that plastic with the green composite, or you took the initiative?
No, they have approached us. Actually, that was a funny story 4 5 years back. Uh, I'll share it with all of you. I got a call from, sorry, I got an email first that we want to collaborate with you and you are working in this area. So kindly provide us your mobile number. So I sent the reply to that email and I sent my mobile number. So after 2 days, I received one phone call on my landline, on my mobile number. Sorry, I sent my mobile number. So on my mobile number, I got that phone call. So in the phone call was from a local number of Roorkee. That phone call was from, so I said, please don't make fool out of me, because you are calling from Roorkee only, so why didn't you come and meet me in my office when you are in Roorkee? They said, sir, no, we are not in Roorkee, we are in a place nearby which is 15 kilometers from here. So we have a plant here, we are manufacturing the chairs, so if you can visit our plant and we want to discuss something with you. So I went there with 1 or 2 students, then we had a long meeting, and then we saw that how all the chairs are made. So we were able to then discuss, collaborate, and then these samples, we don't have this mold here. This mold is a very costly mold, so this mold is with the company. So one of the sister concerns of Godrej, they are in Haridwar, so they are making this part for them, but they are only making the plastic part. So then using the same mold, we made our own material here, because our machine can process 60 grams weight only, and this product is 650 grams. So our machine could process only the samples for tensile testing, compression testing, flexural testing. Then the same material we took there, the fibers and the polymer, and in their machine, injection molding, they had number of machines. So there we used one machine to fabricate these samples. So these samples were approved by the local company here. Then they were sent to Mumbai for their further investigation. So now they are trying to work with different other companies also, because as academic institute, we can only give them the idea and we made them the prototype. So now they are trying to be in touch with other bigger companies which can take this idea to the commercial level, because we can't give them the amount of fibers that they require for making this chair, and fiber treatment and other things is a challenge. So they are now trying to take it to the, as I told you in one of the slides, that commercial viability also is important. So our efforts are at the lab scale only. So at lab scale, we proved that yes, this is a established technology, it can be used. Now it is for them to take. So whatever project cost we asked them, they have given us that amount. So our deliverables, we said we will provide you the prototypes, that we have already provided them.
Yeah.
But yes, one more thing is that this is not the only product where these materials can be used. So if you can change the design of the mold, you can make other products also.
So how much, sir? How much plastic is reduced after making this composite?
Here we were able to reduce 20 to 30%
Okay, sir.
per part.
Per part, yes.
By weight.
Okay. Thank you, sir, for sharing all the process and also one case study and one practical example about the green composite that was made for the company actually. So I am very thankful, sir, for giving your valuable time and for sharing good information. And I am also very thankful to all the participants, those are connected with us till now. Okay. So, sir, we are ending this session. Okay, sir.
Okay, bye.
Thank
Thank
you.
you.